Good afternoon, everyone. Thank you very much for giving me the opportunity to share our work in oxygen electrocatalyst. I'm going to discuss the nickel iron hydroxide nanofiber hybrid and the freestanding electrode. To begin with, the hydrogen demand in 2050 projects to increase up to 20 to 35% in the total energy landscape that account for 460 gigawatt-hour. Now, the green hydrogen from water splitting is a convenient way to store renewable energy. The technology is so ready and flexible that can be implemented at limited scale across the country. However, the anoside reaction, the oxygen evolution, possess sluggish kinetics that hinder the overall performance. That's why our effort is to put into this regime, trying to understand the mechanism and explore suitable material to tackle the issue. In the water electrolysis, there are basically three configurations. The first one is alkaline water electrolyzer that used nickel-based alloy, nickel alloy-based electrode separated by a solid diaphragm working in concentrated alkaline media. This technique is mature and has been implemented in the industry for around 50 years. The second one is the proton exchange membrane water electrolyzer that uses iridium oxide-based electrode on the anode side and platinum-based electrode on the cathode side, separated by a proton exchange membrane. The PAN water electrolyzer working in highly acidic environment, and that makes it very expensive because only titanium plates or porous titanium can be used as support. The last one, the anion exchange membrane, is the combination between the combination of the alkaline water electrolyzer and PAM water electrolyzer that also use nickel or nickel oxide electrode separated by the proton conducting membrane and working in a milder condition, and that makes it a huge potential for upscale. Now, because the catalyst is the heart of the system, there are many development strategies to either increase the active side or increase intrinsic property of the material. However, under realistic conditions, the mass transport is equally important for it to account for high overpotential even with active catalyst use. So with the spray coating approach, we have basically three kinds of losses: the kinetic losses, ohmic losses, or mass transport losses that induced by resistance either within the gas diffusion layer, the catalyst layer, or at interfaces. The nickel iron hydroxide is among one of the best OER catalysts. And here in this illustration, nickel iron layer double hydroxide intercalated by water or carbonate anion. The insertion of iron into the nickel matrix shifts the redox peaks of nickel anodically, and with 10 to 50% of iron doping will account for the best catalytic activity. Electrodeposition is a well-known method to deposit or decorate nickel iron hydroxide at with various shapes, like on different support. Like here is the ultra thin nickel iron flake on the nickel foam, on the carbon fiber, the nano rod on the ITO glass, or nano wire on the FO glasses. In this work, we make the carbon support by ourselves. We convert a lignin into carbon fiber by using electrospinning. And after carbonization, the carbon fiber is set and conductive enough to be used in the sequential electrodeposition. We deposit the nickel hydroxide first on the fiber, and then iron hydroxide to form a nickel iron hydroxide fiber hybrid. The spectroscopic images show the ultra thin flake of nickel iron hydroxide around 3.3 35 nanometer crawl outside the amorphous fiber and uniformly distributed. Here, although we can see some atomic arrangement, the XRD show the hydroxide of low crystallinity due to too small loading on a massive amorphous carbon background. Now, because we already have the freestanding electrode, we would like to test it directly. However, it's very tricky because the entangled structure of the carbon fiber prevent instant gas release. And so we was very lucky to work with Professor Maria's group in Copenhagen to utilize the gas diffusion layer, the gas diffusion electrode for oxygen evolution reaction testing. So this graph here shows that our main material, our main sample, nickel, iron, nitrogen, stand out with the very high mass activity around 2 to 2.5 ampere per milligram, with even a low voltage lower than 1.5 RHE. The taper slope is well defined over a wide range, confirmed is fast kinetic. And one thing that's interesting we observed during cyclic voltammetry is that the oxidation peak in our main sample, nickel, iron, nitrogen, shift cathodically to that of nickel hydroxide sample. And this is something that we never observed in literature before. We move on checking the behavior in various durability tests, and take the SEM pictures afterwards to trace any structural changes. So first, with the normal 15 minutes LSV test from 1.1 to 1.6 volt RHE, we see that on the hydroxide layer which burst after the test. And if we elongate the time to up to 15 hours and narrow down the window potential to 1.5 volt RHE, we see that the catalyst, the hydroxide layer, was suppressed much more without any evidence of metal losing. The continuous chrono amperometry for 5 hours see some detachment of the hydroxide of the fiber, and after around 4.5 hours, we already have a lot of gas accumulated on the surface that account for the disrupt change in the current reading over here. The situation was improved when we introduced 10 minutes interval at 0.8 volt RG. We buy in time for the catalyst to be restored and for the gas to be released. To study trigonometric and coordination structure of the material, we perform X-ray absorption. And here, on the nickel-based sample, our main material, our main sample, nickel, iron, nitrogen, so the lowest disorder factor, which we hint that it have more stable structure. In the iron KH, we compare the iron oxygen bond length of the main sample nickel, iron, nitrogen with that of the nickel, iron, air. And we see we have a shorter bond length, a shorter iron oxygen bond length in our main sample. And this is in good agreement with literature that the metal oxygen motif account for absorption energy of intermediate, and the shorter bond length or shorter motif account for better absorption and lead to smaller overpotential. Now we compare the XPS of 3 nickel-based sample, and surprisingly, we see that the amount of nickel in the control sample nickel iron air is the lowest among others. It's the lowest among all the nickel-based sample, and that hint the nickel-iron ratio on the surface played a key role in dictating catalytic activity. We move on checking the nickel and iron ratio in the bulk, and yes, we can confirm from ICBMS that our two nickel iron sample had similar ratio in the bulk, but have different ratio on the surface. And so when we think back of the sequential electrodeposition during a synthesis approach, perhaps the nitrogen or the gas flow or the airflow contributes to different structure of iron hydroxide upon the nickel hydroxide. Again, we check the XPS of the nickel 2B and iron 2B on the sample, and we see that only in our main sample, the nickel 2B3 shifts to the higher binding energy, which means the nickel center participates vastly in the reaction. And this is not something observed in the control sample. The ICBMS of the electrolyte used in various tests show that higher iron leaching in the control sample than that of the nickel iron of the main sample. And so we postulate that if we have a higher nickel matrix or nickel loading on the outermost of the catalyst, that will have to accommodate back the active iron species during catalytic activity. In case we have iron hydroxide dominate on the outermost layer, the iron hydroxide can't host back the active iron species and result in a higher leaching rate. This is also in good alignment with the dynamic stability reported previously, but we also aware that there may be some other factor that we do not know yet. In conclusion, I hope to convince you that we already have the high active OER freestanding catalyst from abundant resources with little loading. We have some characterization to confirm the important role of nickel hydroxide on the outermost layer of the catalyst that can host back iron and lead to smaller metal leaching. We are seeking further characterization to elucidate kinetic mechanism, to study the performance of the material in various testing systems and improve the material to meet industrial requirements, and also to explore various applications with other hybrid. And I would like to thank our supervisor for the guidance and support. I would like to thank Maria's group at Copenhagen University for a very nice collaboration. Thank our college and the body funding facility I have a chance to use, and thank you very much for your kind attention. And I'm happy to take any question.